Okay, hi everyone. It's just me and Aretha today. We're going to do 8.8 improper integrals day 1 and day 2 today because there's only one worksheet on those. And also we have briefly talked about them and you saw some of those on this last test. Sorry. But we're going to do the notes for those both today. So, I'm sure you guys can see. It says evaluate by using your calculator, so this is just going to be typing these things in, kind of like how we started off yesterday with the limits. And when you put this in your calculator, you may do the into, what is it, integral, integrand, and whatever. Yeah, it's number 9, math 9. Anyway, you just type it in like it looks. And you should get 4.605.
Oh yeah, this is the stuff on test. We were so close.
Sorry, I didn't realize this was on this section. I thought that was the end of it. So the graph 1 over x looks like this. And so what we're integrating is this function from 1, which would be the 0.11, right? And then to the right. And we're stopping in different places as we go further and further to the right. So from 1 to 100, then 1 to 1,000, and then 1 to 1,000,000. And we're trying to see if, much like the limit that we did yesterday, are we approaching some number? Is there any sort of pattern happening here, or is it just, does it keep growing? What's happening? Okay, so let's see, here's such a bad glare. Sorry guys. From 1 to 1,000,000, I get 13.8155. Okay. So based on this pattern so far, or these answers so far, do you think that this converges or diverges? No pressure, it's just you.
So converges means that
It's approaching some value.
they're big jumps. So.
They are big jumps. So it doesn't really look like it, does it? No. So this looks like it's just going to keep growing.
Right.
So we say that that diverges. Now we're going to do the same thing for e to the negative x. Now from 1 to 100, first of all, let's talk about what this graph looks like. The graph shape is very similar. Starts like this, goes down like this, where these values are going to be when, okay, because this is 1 over e to the x, right? So when I have negative exponents, this is really being carried up to the top then. So that would be like e squared, e cubed, e to the 4th, e to the 5th as we go to the left. So it's actually growing exponentially over here. And then down here, right, so that would be 1 over e to the 1st power. So that would just be e. Good. And then 1 over e squared is obviously going to be smaller. And 1 over e cubed is going to be smaller, and so on and so forth. So we're getting closer and closer to 0, but we did that in the last one. So let's see if there's any difference. The integral from 1 to 100 of e to the negative x with respect to x is 0.3678. Okay, so again, we're starting at 1 and we're taking the area and we're cutting it off at different places, right? So we move out. The next one is from 1 to 1,000. And that answer is 0.3678. And the decimal will change a little bit further out, but it starts out the same. And that's a big jump from 100 to 1,000, and not a big jump at all in our answer, right? So, do you think this one diverges or converges? Converges, that's right. It says, to what value does it converge? Do you have a guess at all? Yes. Do you think this represents anything specific or just a weird decimal?
Or is it?
Not really, because we're still talking about area under the curve. So if anything, it's going to get bigger as I go out, right? I'm adding area, but obviously not much bigger.
No.
So what's weird is this actually comes out to
root E or something?
1 over E. Yeah, it's a weird. So e to the -1 or 1 over e is what this is converging to.
Are you supposed to like memorize those values?
No, it would be helpful to know what e is, but I don't expect you to know that 0.3678 yada yada is 1 over e. No. I mean, you could play around with it on a calculator and kind of figure it out maybe eventually, but no. So sketch the graphs of 1 over x and e to the -x, and shade the regions represented by the integral from 1 to infinity of 1 over x and the integral of 1 to infinity of e to the -x. We've pretty much already done that, so you don't have to draw it again. We drew that here, we drew that here. All right, so again, they look really similar, right? So why would they give such different results? So on your graphing calculator, start with the following window from 0 to 5 and y -1 to 2. Then change the window from 100 to 500 and -0.0001 to 0.001. So I do want you to take a minute to do that. So what they're asking you to do is just go into y equals. First you will type in 1 over x for y1. And then in y2, type e to the -x. E to the -x. Hit graph. Now in my standard window, over x looks like this, and e to the -x looks like this. I'm not approaching an asymptote, so keeps going, right? Okay, now let's look with the windows that they gave us. So go to window where it says x min, change the -10 to a 0 and change the x max to a 5. And then the y's are ranged, so change y min to -1 and y max to 2, then hit graph. In that window, there's one.
Do you change the scale or not?
No, you don't have to change the scale. In that window, it looks like this, right?
Mm-hmm.
Okay. So now it might be a little more clear why this one converges, this one right here, and this one diverges, right? First of all, I have all of this extra space, although I'm only starting at 1, so really I'm cutting it off here anyway. But this is more finite, and it's getting closer and closer to 0 faster than my 1 over x is. But now let's look at the window for the second part. So go to window again, change the minimum to 100, x max to 500, y minimum to -0.0001, y max to 0.01. So these y values are going to be super, super, super tiny, right? Okay, what does the first one look like now?
The blue or the infinity one looks like it's going on forever, whereas E is flat.
Right, so this one still has a curve even all the way out at 100 to 500 for x values, right? We still see space here. Now, of course, this is very tiny y scale now, but there's still obviously space. Whereas the other one, that change is so tiny that it doesn't even look like it's changing at all, does it? It looks like it's just a horizontal line. Now, we know that that's not actually the case, but it's close enough that it's approaching a value. So sometimes these integrals, even though they go to infinity, which means they never end, right? Sometimes they could still approach a number. And we'll talk a lot about that throughout BC. There's a lot of those converging, diverging things.
So is it similar to taking a limit?
Yes, it is. It's very similar. Yeah. Because we will have to take a limit in order to evaluate these. So it says integrals such as from a to infinity, negative infinity to a, and negative infinity to infinity are called improper integrals. Basically, it's just any integral where infinity or negative infinity is somewhere in the bounds. Top, bottom, both, doesn't matter. They're evaluated by rewriting the integral as a proper integral and then using limits, which again we talked about right before the test very briefly. So we use b as a placeholder and we say, okay, the limit as b approaches whatever that bound was originally, whatever infinity we're approaching. So it's just kind of a trick because I can't plug in infinity, but I could take the limit. So I force that to happen, okay?
We did that on the test in both those problems.
Yes.
Where infinity was in the denominator.
Yes. And on that last line in that box, where it says negative infinity to c and c plus c to infinity, this is just telling us that it uses the same properties as our normal integrals. Okay, we just have to put a limit in front, but the properties remain the same. Yeah. So we could break it up if we have to, is the whole point of that last line. All right, 1 to infinity of 1 over x dx. Since I can't plug in infinity, I'm going to rewrite this as a limit. So this is going to be the limit as, they use c, it doesn't matter, I'm going to use b. As b approaches infinity of the integral from 1 to b of 1 over x dx. So notice everything is the same except I'm taking the limit as b approaches infinity instead of sticking an infinity up there. And I know this is x to the negative 1. When I integrate, I add 1 and I divide by that new exponent. In that case, it would be x to the 0 divided by 0. So what does that remind me of? The integral of this is what? So the limit as b approaches infinity, and I'm going to go ahead and integrate this like normal. This is the natural log of x from 1 to b. The system, the method is pretty much the same as any other integral. So I plug in the top bound, limit as b approaches infinity of natural log of b minus natural log of 1. So top bound minus bottom bound. And what would the natural log of b be approaching as b approaches infinity? Remember what the graph of natural log looks like.
It's similar to, does it go down instead? Because it's similar to E, right?
It is related to E because it has base E, yes. But when I take logs of bigger numbers, I'm gonna get a bigger number. So, and that's because natural log E of whatever x is equals y. E raised to whatever that number is equal to that, right? So I'm saying when I plug in 1, y would have to be 0. So when x is 1, y is 0. Okay. When I plug in 2, well, that would be e to the something equals 2. When I plug in 3, e to the something equals 3. 4, e to the something equals 4. So I'm going to have to raise e to larger and larger numbers to get these bigger and bigger x values, right? But I can't plug in 0 here because I can't raise e to anything and get 0. Even if I plug in negatives, right, I'm just dividing by e. So I can get smaller, but I'm never going to actually reach 0. So as it gets smaller, I'm getting closer to 0, and then it's just going to keep growing. Now, is there an end to that growth? No. It doesn't grow very quickly because of, yeah, this is just exponents. But it does keep growing. There is no end. I can keep plugging in larger and larger x's, and I'm going to keep getting bigger and bigger y's. So because of that, as b is approaching infinity, my y values are also approaching infinity. So essentially this is infinity. Yes, minus 0. Which we can't say equals infinity, right? Because that's not really a value. But I could put one of those little arrow things. So it goes off to infinity, which tells me that it diverges, which is what we found anyway, right? We found that there's no pattern, and this is how we would show that.
What is this used for, like, to measure or calculate? Is it?
Well, sometimes you will have to integrate things to the end. There's not really an end if we're talking about approaching infinity, right? But if we want to know the area under a curve, because a lot of times that represents other things, like if we talk about original function being, let's say, acceleration, and I want to know the velocity from here to here. And from here to infinity, like with no bound, then I would have to have the function itself and integrate to infinity. So, I mean, there are times when we need the areas under the curves without a bound. Yeah.
Okay.
Also, if I need to know, like, is there a pattern? Am I approaching one thing, or is this just going to keep going?
Okay. Makes sense. And it's
I can't think of anything more specific right now, but I'm sure we'll see stuff. Okay, sorry. From 1 to infinity of e to the negative x dx. Alright. So, only difference is I'm going to change this to a limit. I'm going to keep using b because I like to. I don't like using c only because we use that integrals to mean our constant a lot. So, I don't know. You can though, as long as you're consistent with what it means. So the limit as b approaches infinity, the integral from 1 to b, e to the negative x dx. So I know the integral of e to the u is e to the u, right?
Right.
Right. So the only difference here is I'm going to need a negative in front. But I still have the limit as b approaches infinity. Negative e and the u remains the same. From 1 to b. So now I plug in top and bottom. Negative e to negative b minus negative e to negative 1. Okay, I'm going to rewrite this because I don't like having those negative exponents. So I'm going to rewrite this as a limit as b approaches infinity of negative 1 over e to the b plus 1 over e. Okay? Now, 1 divided by something raised to an infinite power. Yeah, it's approaching 0. It's just getting bigger and bigger and bigger. As I divide by something bigger and bigger, this is going to approach 0. So really I have 0 plus 1 over e. And that's how I end up with just 1 over e. Which again is what we were seeing when we were plugging it into the calculator too. So that's good. So we say it converges to 1 over e.
So for these types of problems, will we have a calculator with us? Or will they
Not always. Like that one, we should be able to do without a calculator. Well, the one before too. Same thing with this next one. Yeah, which you'll see it enough, you'll get pretty good at it. And also, if I'm not confident, I'll just make like a tiny little table and plot 2 or 3 points, and I'm like, oh yeah, it's doing this. So. All right, so this is the issue, right? We're gonna make the whole limit. This time we're approaching negative infinity, and it's on the bottom. So from b to 0, e to the x over 4. So again, I would use substitution just to be safe here. You're probably pretty good at it by now that you might not have to write it out every time. But yeah. So if u is x over 4, then the du is just 1/4 dx. When I multiply to the other side. So if I were to rewrite the whole thing, just for clarity. Of e to the u or du, right? So I keep carrying this limit around, but I know the integral of that is just, which I could pull the 4 out still, or I can put it inside, it doesn't matter. I can even pull it out in front of the limit. Remember with limit properties, if I have some coefficient, I can pull that out front and multiply the limit by that coefficient. So I could put the 4 here, I could put the 4 here, or I could put it in here. It doesn't matter. It's just a matter of distributing it or not. And then the integral of e to the u, I'm going to go ahead and substitute back in that x over 4. So 4 e to the u, in this case x over 4, from b to 0. And now we're plugging in. So limit as b approaches negative infinity, 4 times e to the 0 over 4, or just e to the 0, minus e to the b over 4. And we did that, so we're taking the limit up, right? Is that the bottom? Okay. All right. So I'm going to pull out the 4. Yeah.
I mean, it doesn't make much.
No, it doesn't. I just don't want to have to think about it right now. I'm taking the limit. That's all it is. So e to the 0 we know is 1, right? And this doesn't affect that at all. So I just have 1. minus. Now I'm taking the limit as b approaches negative infinity of this. So as e approaches negative infinity, since my value is getting more and more negative, I'm really talking about 1 over e to the negative b over 4. But now, if I am approaching negative infinity, this negative in front of it is positive infinity. And if I know 1 over some number raised to something approaching infinity, it's just getting larger on the bottom, which tells me what?
Approaching 0.
Approaching 0, that's right.
So,
Now, had it been approaching positive infinity, this would be divergent, right?
Mhm.
Because I would just have e to something approaching infinity. But that negative, since it's taking it down to the bottom, it's actually approaching 0. So now I'm taking the limit so I don't have to carry that limit piece around anymore. Equals 4. So we could say it converges to I'm going to break this up just so I don't lose a bunch of stuff.